So from the programmer's perspective, from each individual process's perspective, there is just a sequence of memory addresses. Now I'm drawing low addresses on the top, going down. These are virtual addresses, and the operating system arranges for some of these addresses actually to be in memory, and maybe some of them are in disk. And there's no constraint that the order that things are in virtual memory corresponds to physical memory. For example, hex A4000 in virtual space might be mapped to the physical memory that starts hex 3000. Meanwhile, the next block, the next page of virtual memory might be mapped to a lower address in physical memory, and so on. If we have a pointer in our virtual space, so let's suppose in this page, the A4 page, we have a pointer value A60B5. Maybe this is a variable that refers to some malloc memory or something like that. When this memory is stored in physical memory, it's not like this address changes to a physical address. Right? The copying of pages into physical memory, there's no way to know which of those numbers were meant to be used as pointers and which of them were strings or opcodes for machine code or whatever. But that's okay, because any use of this pointer by the CPU will again go back through the virtual memory mapping, which will say, oh, that data resides at this point in physical memory. So what that means is, for the most part, you can completely ignore this issue of physical memory and whether it's on disk, and just live in your virtual memory world, and it's up to the operating system to take care of things. It doesn't matter to you that this view of virtual memory is a complete fiction. The blue boxes don't exist at all. They are just represented by the page table, which maps the few upper bits here of these addresses to various other pages. On the other hand, the fact that there is virtual memory is something you can take advantage of when you want to. And the first feature to take advantage of is that most pages are not mapped at all, especially in a 48-bit space represented by 64 bits. Very few of the addresses are actually matched. And that is nice in the sense that if you accidentally use some other number as an address, if you try to access some memory on this page, hex A1000, but that page is not mapped at all, then you can get a seg fault, which is, usually you think of a seg fault as a terrible, mysterious error, but at the machine level, or where you're thinking low enough, then it's actually a very friendly sort of message. Instead of just making up data, it's telling you, no one's ever said that this virtual memory should be mapped. So that's a benefit. That's why when you accidentally use a null pointer, you get a seg fault instead of random data that happens to be mapped to page 0, because it's a good convention to not map page 0, and the operating system enforces that convention. In addition to whether a page is actually mapped, as represented by the green backgrounds here, then a virtual memory system can keep track of extra information, like whether you intended for pages to be executable or writable. For example, if you accidentally try to write to a page that holds the code for your program, the machine code, that's generally not what you meant to do, and it's nice to get a seg fault error to say, it's an error because you're writing to the code page instead of randomly changing the bits of your program and getting very confusing behavior later on. Or on the other side, if you have some memory that is meant to be writable, then that's probably not code that you meant to execute. So if you accidentally jump to that code, if you malloc some memory and jump to it, then that was probably an accident of some sort, maybe even an attack. So getting a segmentation fault is, again, a nice result from the operating system, instead of getting random bytes executed as code.